Good morning. My name is Xinhao. I'm a second-year PhD student from Duke University. I'm very glad to give a talk on our paper, Understanding RDMA Microarchitecture Resources for Performance Isolation. This work is in collaboration with my colleagues from Duke, Microsoft, and Shanghai Jiao University. Today, we have witnessed the rapid adoption of RDMA in cloud. The kernel bypass and hardware offloading features enable RDMA to achieve low latency, high throughput, and high CPU efficiency. And people use RDMA almost everywhere in the cloud to get its benefits. So given the success of RDMA deployment, cloud providers naturally want to push these benefits, push the RDMA to public cloud. However, public cloud brings unique challenges. There can be multiple tenants, and these tenants' behaviors are uncontrollable and unpredictable. There can even be a malicious tenant who tries to deliberately impair others. This means to empower RDMA in public cloud, we must have performance isolation. Fortunately, we have many existing solutions. For example, some RDMA NIC provide hardware-based isolation, and people also invent some software-based isolation solutions for RDMA recently. Now, let's imagine if we are network operators. We pick and enable one solution, and we want to use this solution to ensure that two tenants can fairly share the networks. What should be our next step? Naturally, the next step is to evaluate this isolation solution. But how to do that? We take a look at how existing solutions evaluate their isolation effect. Today, the state-of-the-art approach is to use a traffic generator to test performance isolation. For example, they usually run a benchmark workload as a victim tenant and use traffic generators such as iperf or perftest to exhaust the NIC bandwidth. In this way, they test if the isolation works by checking if the victim's performance is affected. Now we know how to do that. Let's just run iperf and perftest as the attacker to exhaust the NIC bandwidth. And we observe that the attacker who tries to generate a lot of traffic still only gets half of the bandwidth and won't impair the other tenant. We are quite happy, and we feel that this isolation solution is perfect, and we are ready to deploy this solution to the production. Is that the end of the story? Not yet. We have a however here. Actually, we observed that some fancy traffic pattern can cause isolation violation very differently. For example, an attacker may have some specific traffic pattern which only consumes less than 1 gigabit per second bandwidth, but the victim's throughput drops drastically because of the attacker. We will explain this case later with more details, but here, the high-level takeaway is that existing isolation tests have very limited coverage. And therefore, we need to have something that can cover all these cases and systematically evaluate RDMA's performance isolation. To do so, we first need to understand why RDMA can have these special violation cases. The key reason is that RDMA has very unique microarchitecture resources contention. Compared with traditional networks, RDMA has much more complex microarch resources. For example, besides the network bandwidth, RDMA has only cache, has processing units, and etc. And all these microarchitecture resources are very critical to its performance. When microarch resource contention happens, tenant's performance can be affected unexpectedly, but also very severely. Now, we briefly introduce how these microarch resources are involved in RDMA communication and why they are crucial to RDMA performance isolation. Let's see an outbound example. So we want to send 1 megabyte message to the remote end. In RDMA, to send a message, applications need to post a work request through this IBV post-send API. And the NIC will process the request. During the processing, it needs to access some metadata. For example, it needs to read the translation mapping to translate the virtual address to physical address so that it can do DMA to read the payload from the host. These information are usually stored in the NIC cache. However, if a cache miss happens, the RNIC needs to issue extra PCIe operations to fetch this metadata from the host DRAM, which potentially can cause performance drop. When there is no cache miss and everything looks good, the application should reach almost full link speed. That's great. Now let us assume there is another tenant join the network and call some specific type of RDMA operations, let's say a verb call alpha here. This operation may require the RNIC to access some translation data as well, and thus heavily consume the NIC cache. This will cause the NIC cache to thrashing and make all tenants suffer from heavy cache miss. and ultimately cause some tenants to suffer from end-to-end performance drop, such as the blue tenant here, whose performance dropped from 100 gigabit per second to 10 gigabit per second. This microarch resource contention indicates that in order to achieve, in order to evaluate performance isolation systematically, say build a systematic test suite, we have to take all these microarch resources into consideration. To achieve this, our key idea is to design a set of workload pairs so that these pairs can contend on some particular resource individually, such as the TX pipelines in this diagram. In this way, we can evaluate the performance isolation by checking if they work well under all types of microarchitectural resource contention. Our first step is to identify what verbs are related to which type of resource contention. We achieve this by leveraging modern RNIC feature, hardware counters. These counters provide some information about RNIC internal resource usage. They do not provide very accurate or detailed usage info, but we find these counters are already sufficient enough for us to extract the relationship we need. For example, we can keep calling an API called IBVRegMR to register memory regions. This API will translate the virtual address to physical address and update this address mapping to the NIC. We monitor all counter values when calling this API, and we observe that some specific type of NIC cache, the counter will increase. And now we know that this kind of verb is consuming this type of cache. And this qualitative relationship is actually what we need. Our next step is to leverage these relationships. We now know which type of verbs operations may contend on which type of resource. We then generate tons of workloads that calling these verbs with different parameters and patterns so that they contend on the same resource. And we test all these traffic patterns using a victim-attacker scheme. For example, we pick one workload as Husky victim, and we let other workloads serve as Husky attacker. We run this victim-attacker pair together, and we measure if the victim's performance is affected. In this way, we successfully get a set of workload pairs that are contending on particular types of resources. For example, some traffic pair contend on text pipeline, and some contend on NIC cache, and etc. And this traffic pair together construct our test suite. Each pair in the suite targets on a specific microarchitecture resource. Next, we will present some interesting results we get by applying this methodology. Before doing that, here is the brief description of our testbed. We first conduct study on Mellanox NIC, and then we generalize these findings to other types of NICs from different vendors, and we see they are all valid. This is the full list of our findings. All of them are described with abundant details in our paper, but unfortunately, due to the time limit, I can only discuss 2 key findings here, which we feel most interesting and most unexpected. The first one is memory registration cause severe cache contention. Let's say we have a regular RDMA application who access many different memory regions. It achieves the full line rate with a small amount of cache miss because of its wide access range. This amount of cache miss does not reduce the performance much because RNIC internal pipeline already has some optimization that can hide such overhead. Then we let another tenant try to keep registering and deregistering the memory regions. Note, this red tenant does not send anything at all, so it consumes 0 bandwidth. But we observe that such memory registration and deregistration also need to access some translation data, so it frequently accesses some particular type of NIC cache. And in this way, it can cause that NIC cache to thrashing and cause heavy cache miss, which ultimately cause the victim to suffer from severe performance drop. We want to emphasize that intuitively, such an attacker who does not send any network traffic at all should have negligible effect on the other tenant's network bandwidth. However, such performance interference actually happens because of this kind of cache contention. This is very out of expectation. Another finding is about error handling exhaust RX pipeline. Before we discuss this case concretely, let's quickly review how send-receive work in RDMA. To receive the payload in RDMA, the receiver needs to post some receive requests. When incoming send requests arrive, the NIC will consume the posted receive request to process the incoming request. As this figure shows, everything goes correctly. However, if the receiver does not post any receive request at all, an error called receive not ready will be triggered. The RX pipeline will handle such errors and discard the incoming send requests. What we observe is that if at the same time there is another tenant have incoming traffics, say this blue tenant, this tenant's traffic will be all blocked, no matter what types of workload it is. For example, if we let the victim to be a simple write traffic, for example, generated by the perf test, its performance can drop from 97 gigabit per second to almost 0 when there is an RR attacker. This is quite a catastrophe. And these findings led us to design the first test suite for RDMA performance isolation. We name it Husky. It contains a set of attackers targeting on different resources and victims that are sensitive to different resource contention. With this test suite, we evaluate 3 existing state-of-the-art solutions, including 2 hardware-based solutions like separate hardware traffic class and SILV, and 1 software-based solution, Justitia, which is accepted to last year NSDI. We first present an example of synthetic workload test. The attacker is the receive not ready error attacker we mentioned before, and the victim is a simple perf test write traffic. The victim always achieves line rate without attacker. We configured all approaches to let tenants fairly share the network, so each of them should get 50 gigabit per second bandwidth. And whoops, when under all attacks, the victim's traffic will still drop to almost 0 when under all types of isolation solutions. This shows the power of microarchitecture resource contention. Now we present another example with real application, an RDMA-based all reduced traffic. And in this test, we also try to combine all the isolation mechanisms as best as we can. For example, we enable both SILV and hardware traffic class together. We didn't enable all the 3 isolation solutions we mentioned before because currently, Justitia is not compatible with SILV. And we compute the expected threshold based on the isolation settings, shown as the red line in this figure. We can see that this powerful combination can provide some isolation, like prevent the bandwidth attacker, but yet cannot prevent our attacks that target on those microarchitectural resources. We also learned several key lessons from this long journey. One of the key takeaways is that RDMA performance isolation is much more than only bandwidth and packet rate. So to evaluate RDMA performance isolation, you cannot just simply run iperf or perf test and say, oh, that's perfect. And this project also shows that targeting microarchitectural resources can violate performance isolation more easily. For example, to violate performance isolation, you don't even need to generate any traffic. We also see that application sensitivity for resource contention are quite different. This means maybe in the future, we need to consider how to write a tenant RDMA application in the public cloud environment. We are also very honored to see our Husky test suite already achieve many impacts. It first provides value to hardware vendors. All our findings are acknowledged and reproduced by the corresponding vendors. Besides, vendors like NVIDIA already provide multiple firmware upgrades as solutions to addressing the issues we found. We are very, very grateful to that. It also provides value for NIC users. Our collaborator Microsoft already used this test suite for their RDMA testing. Besides, our tool is general. It does not rely on any specific NIC type. And here are our current user list. Please try it if you want to test your RDMA performance isolation. To conclude, in this paper, we argue that understanding RDMA microarchitectural resources is crucial for RDMA performance isolation. We conduct systematic study on these microarchitectural resources and present insightful findings. More importantly, we built Husky, the first test suite that evaluates RDMA performance isolation, which sets a higher bar for RDMA solution. Our project is open source at this link. I will end my presentation here, and I'm happy to take any question.